Hello, my name is Lukas Kasper. I am researcher at the Institute for Energy Systems and Thermodynamics at TU Wien, and in this video I'll introduce you to HyStEPs, a novel hybrid storage prototype for efficient processes. Decarbonisation, and thus mitigating ecological damage to our planet, is seen as one of the grand challenges of the 21st century. While we are making progress regarding renewable energy supply, new complications for industry arise. Renewable energy sources are very volatile in their nature. Contrary to that, industrial energy demand is bound to process requirements. In order to decouple energy supply and demand for industrial processes, the integration of thermal energy storage is a solution of high relevance. With the help of such storage, the mismatch between supply and demand is no problem, and overall energy consumption can be reduced. However, energy storage demand is expected to increase even more in the coming years, and it's not very cheap either. This is why we came up with a novel hybrid storage concept to retrofit existing storage. This solution has no need for further alteration in existing process infrastructure and is also expected to reduce investment cost compared to conventional technology. The first element of this hybrid storage is a typical root steam storage, or short RSS. This storage type is very common in various industry sectors such as pulp and paper, food and metal manufacturing. The storage is charged with hot steam, which increases the pressure inside the vessel. The steam thereby condenses to liquid water and the filling level rises. When discharging, the pressure in the vessel is reduced, leading to the water being evaporated and leaving the vessel again as hot steam. The RSS is a sensible thermal energy storage, meaning that there is an almost linear dependency of storage temperature and the thermal energy stored. Contrary to that, a latent heat thermal energy storage, which uses phase change material, or short PCM, can store a high amount of thermal energy within a small temperature range, the temperature phase change, and thus achieves very high energy densities within the operating region. The basic hybrid storage idea is now to simply mount modules filled with phase change material on existing RSS vessels to increase the overall storage capacity. However, as simple as this basic idea may sound, the realization is of course not straightforward. This is why the Austrian Climate and Energy Fund provided resources for the project HyStEPs. For about 3 years, our project partners and us tried to work out how to build the best possible hybrid storage. To give you a glimpse of understanding the difficulty in this, just know that there are a lot of distinct features that need to be optimized. The hybrid storage design should allow for high heat transfer rates between steam and PCM to achieve high charging and discharging power. Of course, heat losses need to be minimized to maintain high efficiency. Also, the state of charge estimation and control is a very difficult task, but at the same time crucial for optimal storage operation. High safety and durability standards, as well as mechanical resistance and stability, have to be met to allow for long-term industrial application. And last but not least, the hybrid storage design should be economically viable. It is to be said that, more often than not, you have to acknowledge trade-offs between these individual features. My colleagues and I started off the project with developing a high-fidelity thermodynamic model of the PCM modules, which considers heat transfer through both heat conduction and natural convection in liquid PCM. This model was successfully validated and then used to numerically study the storage behavior in order to find the optimal design of heat transfer enhancement configuration. Furthermore, we developed a co-simulation approach to couple the models of PCM modules and RSS to allow for simulation studies of our hybrid storage design. Together with our colleagues from the Institute of Mechanics and Mechatronics at TU Wien, we then elaborated how to reduce computational complexity of these modeling methods by a significant amount. Thus, we achieved real-time capable simulation of storage behavior while maintaining very high accuracy. We then used this model to develop an efficient observer approach, allowing for the estimation of state of charge and location of the melting front within the PCM modules. This is the foundation for optimal control of the hybrid storage during operation. After deciding on a final design, we began construction of a lab-scale prototype of the hybrid storage. The test rig is located on site of our project partner voestalpine in the city of Leoben, Austria, in one of the largest steel manufacturing plants in Europe. You can see here a simplified sketch of the RSS. It features a pressure vessel of about 1 cubic meter of volume and operates at up to 25 bar absolute pressure. We mounted a total of 8 PCM modules to the RSS vessel, 4 on each side. These were filled with roughly 20 kg of lithium nitrate, sodium nitrate, which is a phase change material with a melting point at around 192 degrees Celsius. The modules were tightened to the pressure vessel with metallic springs. On the right-hand side, you see the final storage setup, including its heat insulation. During our meticulous experimental investigations, we recorded data of over 50 PT100 temperature sensors in the PCM modules alone. This measurement data helped us to describe the thermodynamic characteristics of our prototype in actual operation. What's illustrated here are 2 temperature measurements in each of the 8 modules for an RSS temperature trajectory that is given below. During charging as well as discharging, we found significant differences in the behavior of the modules, which we thought to behave quite similarly. Some of them achieved very high power, whilst others did not. This led us to critically reflect on some design choices, since heat transfer between RSS and PCM is even more crucial than we thought, and deviations during manufacturing have to be considered as well. So let me quickly recap the results of our project. We developed the tools to model both the RSS and the PCM modules with very high accuracy for various operation and design considerations. Thus, we laid the foundation for design optimization and also state estimation and control, which is essential for optimal hybrid storage operation. We built the first ever prototype of this hybrid storage, achieving more than 30% storage capacity increase compared to the RSS alone. All this while ensuring very high safety and durability standards. With the help of this test rig, we learned some lessons and made some very essential findings for further research and development. For example, we found that heat transfer between the RSS and PCM modules is even more crucial to charging and discharging power and even more difficult to manage than we thought. We made some very promising results, but further design iterations seem to be necessary, especially to arrive at a profitable and scalable concept. The good news is that we already have ideas on how to solve these issues, so please pay attention to our future research. If you're interested in the work summarized in this video, feel free to check out our publications. And if you have any questions at all, please contact me or the head of our department, Professor René Hoffmann.